So this is bioinformatics and genetics. So in today's class, we discuss about probabilistic models of evolution, and then we discuss about the phylogenetic trees. We have a short introduction, and then we discuss about substitution probabilities as well as evolutionary rates. Then we discuss about the rates of evolution, the data likelihood, optimal trees and learning, and then we discuss about parsimony and some extensions to that particular topic. So this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, let me thank God for giving me this golden opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students, and young researchers. So in today's session, we will have a short introduction, then we will have some trees, then we discuss about some probabilistic models, about the substitution probabilities and evolutionary rates, then we discuss about the rates of evolution, then we discuss about some data likelihood, and then we discuss about the optimal trees and learning, about parsimony, minimum mutation, and about the evolutionary models for hidden Markov model, and finally we end this class with the extension. So I have given the independent work as well as the open-ended project work in the Google Classroom. Maybe after this class, I will explain you how you should do the open-ended project work. Okay. So at regular intervals, I'll be giving you some short videos to discuss the knowledge in our topics. Fine. So this is a short introduction to what you have with the evolutionary relationship between different organisms. So there is evolution which is taking place in and around every point of time. So maybe if it is a living organism or maybe some extinct organism like dinosaur, everything we will have a evolutionary relationship. For example, they say there is a relationship between what you call a lizard and a dinosaur. So they say that DNA sequences are interrelated. Have you heard about it? There is some relationship between a lizard and a dinosaur. You have heard about it? There is some evolutionary relationship. So actually it comes from the morphological or maybe chemical characteristics at the time of the Darwin's theory. Have you heard about Darwin's theory? Darwin. Have you heard about it? Darwin. Yeah. What is Darwin's theory?
This people came from the
evolution. Theory of evolution. Human beings come from monkey. Like this. Okay, so this is Darwin's evolutionary theory. So this is phylogenetic trees where we'll actually generally derive it from the DNA as well as protein sequences. So generally, maybe if you take maybe elephant like mammoth, maybe it was extinct maybe years, thousands of years back. Maybe dinosaurs have been extinct 10,000 years ago. So maybe it is mapped to its DNA, and generally for deceased humans, we will have several family relationships. We'll take the consideration of a case study. There is a proof of identity of the last Russian Tsar. His name is Nicholas II, and maybe we will have the story of Anna Anderson, who claimed she was Tsar's missing daughter Anastasia. So that's what even with the case of the DNA sequences, we can actually come up with various evolutionary relationship, and we can actually find out who is the real parent, who is the real child. That we can do. So the bones of the Tsar has been lying in the soil since 1918, and even the literature, it has been inferred from several phylogenetic trees from sequence data. So maybe we will categorize into two methods. One is parsimony method, and then we have likelihood method. Likelihood method is actually based on the probabilistic model of the evolutionary process, and this likelihood method is actually used in connection with the probabilistic model. Okay, but parsimony methods, it is actually comes from the rate of evolution. Okay, so generally we are actually discuss about the Cox-James axioms. Okay, so generally it comes from the Bayesian networks, where we generally begin from a probabilistic model of evolution. So generally, if you consider tree, generally tree is nothing but, if you see outside, a tree is a connection of branches. Similarly, here a tree is a connected acyclic graph. As you see in the diagram, we have every 2 points which are connected by a unique path. For example, you will have graph which are having like with the cycles, okay, and then we will have tree with no cycles which are connected. Similarly, we have a forest, no cycles, and they are not connected even. So a tree is said to be binary if each vertex has either one or maybe three neighbors. So a tree is rooted if a node has been selected and to be termed the root. So we will have almost like connected trees with graph, or maybe you can have a tree maybe with no cycles but it is connected. Similarly, you can have forest which are connected but they are connected only for themselves. It is not connected as a whole. So every thing, for example, if you take in the case of maybe you are a child of so and so, maybe you will have some ancestral properties. You will have the properties of your parent. Your parent will have the properties of your grandfather and your grandmother. So everything comes from the ancestral sequences, and both they will have rooted sequence as well as unrooted sequence. They are said to form a topology. So topology you can consider is a branching pattern of all the sequences in the tree from the time of the divergence. So these are the probabilistic models. These are mathematical models. So evolutionary theory comes from probabilistic model, and probabilistic model will have a variation of a dice model. Okay, so we'll have an ancestral sequence. We'll have a randomly distributed evolutionary process. So we'll use the Markov process. We'll have p y x power I of t equal to probability of xi of t plus s, that is the variation, okay, of the simple dice model, equal to y of xi of s is equal to x. So it's actually independent of this s value and t value, so it is greater than 0. So it says that for each position of I there is a probability. The probability is actually p yx of I of t, such that this x is actually substituted for y for this time period t. So this is the substitution probabilities and evolutionary rates. We'll have the point accepted mutation to be limit t tends to 0, py x of t equal to del of y comma x. So it holds true for 1 if y is equal to x. That is why we said in the previous slide y we substitute in place of x, okay, and 0 otherwise. So we denote this p of t equal to p y x of t, okay, for which we can define the initial value p of 0 equal to id. So id is nothing but the identity matrix. You can categorize it as a cross a, okay, a cross a. So this is actually taken from the mathematical functions, where we will write p of t equal to p y x of t. So this q factor will have equal to p dash of 0 limit t tends to 0, p of t minus id. Id is actually the identity matrix divided by t, okay. So p dash of t is actually q into p of t equal to p of t multiplied by q. So we can come up with the from different assumptions from these mathematical models. So actually evolution, it actually comes from the substitution. We substitute y in place of x, and without this insertion and deletion we will have all the sequences should be of the same length. Also the substitutions, it is independent of each other. And next one we will have Markov property, where you have the substitution probabilities which depend only on the current state and not on the past experience or maybe the past history. And then Markov process is the same. We repeat the Markov process for all the positions. Okay. Then we have the rate of evolution. We have the rate matrix Q, which is defined by a multiplicative factor. So P of t is equal to exponential Q of t equal to exponential lambda Q t by lambda for any lambda equal to 0. So lambda you can call it to be the substitution rate per unit time, and you can choose this probability P equal to P of x. So wherever we have x, we can substitute the y. So that is actually the substitution probability. So this is the thing, p y of y x of dt equal to 1 minus lambda dt del of y comma x plus lambda dt py. So actually you can categorize it as a matrix Q. So Q XX equal to lambda Px minus 1 and Qyx is equal to lambda Py. Okay. So Pyx of t is equal to e power minus lambda t del of y comma x plus 1 minus e power minus lambda t Py. So generally it can be given as an arbitrary or maybe imaginary stationary distribution where we will have relationship between different probabilities. So this one we can formulate different mathematical models for the matrix Q, and we will substitute for, in place of x we substitute for y, and we repeat this same Markov model. Then we will have data likelihood. So in the case of machine learning, we will use this phylogenetic trees. So everything it is dependent on the rate of evolution, which comes from the a probabilistic model. Okay. So generally we will assume k sequences for the alphabet A. Everything will be having the same length n, and we will have a tree T. So that is actually a phylogenetic tree. Generally it will have a root, okay, R, and then the time length dji between different adjacent vertices I as well as j. So for this we compute the likelihood. Likelihood you can term it as P of O1, O2, O3 up to OK slash t. So that is actually you are going to categorize this particular likelihood according to the Markov model. Okay, so we will have the column positions P of O1, O2 up to OK slash t equal to pi of k varies from 1 to n. This likelihood P of O1 power k up to O2 power k, O3 power k up to OK power k slash t. So it is actually multiplication of factors. It is not given summation. It is given pi. Pi means it is multiplication. So this is OK. It's actually OKJ. Actually represents the kth letter observed in the jth sequence. Okay, so it's a tree. It's actually a phylogenetic tree. So it comes from the Bayesian network. So Bayesian network actually comes from the hidden Markov models. We will have a tree structure where we have a conditional probability of node J. Okay, we have I, the parent. I is the parent, and node is actually the J. Okay, so we'll have the time distance dji, which is of the form P of xj equal to y, and P of xi equal to x equal to P of the multiplication property. So it is P of yx of dji. So this dji is nothing but the distance between the ith parent and the jth node. Okay. So this is the tree rooted at R with possible alternative root, okay, from R to J branch. So from this one we'll have xi, xj. From I it goes, we have a node which is S. Okay, so from I to R and then R to J branch. So we'll have several optimal trees as well in the case of hidden Markov model. So for this we'll have the expected maximization step. I think in the previous class I discussed about E step and then M step. So it is actually EM step I discussed this one. So it is actually coming from the gradient descent equations for the optimization of the length of the branch. So we'll have optimization of the topology, which generally requires approximations. For example, even if it is rooted or maybe unrooted, we will have some topology where we will have exponentially large, which is growing in size. Okay, and also there is one heuristic algorithm which has the progressively adding species or maybe observation sequences. Generally it will be considering in a two species tree. So a new species is being selected, and all particular positions with respect to the current tree are being considered. For example, here we consider an optimal tree where we will have a greedy growth as well as a greedy phase as well. Okay, so in this search algorithm, of course in the case of phylogenetic tree, it comes from the Bayesian network. So from the greedy growth, like here if you see in the diagram, it has maybe a parent, it has children. Okay, so from this it is going to a greedy phase where generally we will have mutations or maybe evolutions coming from each of the root. Okay, so it's more intensive, and generally in addition to the priors, it requires integrating across the trees. Generally you can estimate the probability function for each of the methods. So generally, as I told you, there are two methods. One is parsimony methods and another one is likelihood method. So parsimony method, generally it is considered to be a fast evolution method. Generally we can use in the machine learning. Okay, so for this we will have the MDL, minimum description length, and we will calculate the parsimony cost or maybe parsimony error of the assignment. So we'll have EP of xi slash t equal to, we'll have double summation, one for I and another for j. So I belongs to I and then j belongs to n plus I. So it is del of xi comma xj. So actually this error, parsimony cost or maybe parsimony error, is given as a non-identical substitution. In the earlier methods, we had identical substitution. For x, we substituted y, but this one, it's a non-identical substitution. And generally, we have to compute the tree with a minimal cost. So actually, we find the distance to be less and the cost is also to be less. Okay. So this minimal assignment is given as the minimal mutation fit. And we find out the sequence of the estimate. So we'll have P of xi slash t equal to PR of xr. We'll have I belongs to I and then j belongs to n. So we'll have P xj xi of dj. So we'll also have the negative log probability, which is E of xi slash t. So this negative log probability is given by minus log. Okay, PR of xr minus summation the log of the previous thing. Okay, so it is minus summation I belongs to I, j belongs to n, log of p of xj xi d of ji. So it actually comes from this one, p of y x of dji. So this it comes from. Okay, so generally we will have p of xj xi of dji equal to a if xj equal to xi and 1 minus a slash a minus 1 if xj is not equal to xi. Okay, so similarly we will have this exponential function or the probability for e is equal to alpha e power p plus beta. Okay, so we'll have this alpha to be greater than 0 and we'll have the beta such that e equal to alpha e power p plus beta. Finally, we go with the minimum mutation. For any tree, we will be categorizing the Viterbi code for the assignment of the YAML phylogenetic model. So if the amount of change, if the rate of change is actually small for the evolutionary times being considered, then we will actually go with the parsimony methods. Okay, so for the case of parsimony, we will have weighted parsimony. So we can go with the assumption of uniform substitutions. So we'll have P of y x of dji is equal to e power minus alpha w of y comma x divided by summation j belongs to a e power minus that same thing in the numerator, same thing we'll have e power minus alpha w of z. Here we'll have a change of parameters z comma x. So as I told you, parsimony methods, we have both the weighted as well as unweighted methods. So parsimony methods generally, when you compare it with the machine learning methods, it's much more faster. And generally, that is the reason parsimony methods are being widely in use. So maybe if you can compare this machine learning methods as well as parsimony methods, generally, if you this artificial data which is generally generated by the probabilistic evolutionary model, with the case of this one, parsimony methods are greater, faster, and actually widely it is being used. So as I told you, with the case of phylogenetic trees, it comes from the evolutionary model. So phylogenetic reconstruction is actually an application of the Bayesian models, and from this we generally tend to evolve the evolutionary probabilistic model. Okay. So for this case, we use the Markov substitution models, which actually forms the class for this evolutionary model. So in the case of parsimony methods, we will have several algorithms, and we tend to use hidden Markov model for for the both for evolution as well as with the strength as well as the weaknesses. So here evolutionary models are needed to regularize this hidden Markov model, and generally we can have emission probabilities with the case of larger databases. So this is the evolutionary model for hidden Markov model for the case of xt minus 1 xt. So from xt is actually the current state, xt minus 1 is the previous state, and xt plus 1 is the next state. Okay. So similarly with the case of the factor yt is actually the current state, yt minus 1 is the previous state, and yt plus 1 is the next state. So we'll have like trees, we'll have alignments, phylogeny, as well as the structure which comes from the probabilistic models. So the Markov substitution process is actually an evolutionary model. We have evolutionary times and we'll have a stationary equilibrium distribution. Okay, fine. So this is the two states. We'll have x1 and x2. So we'll have v1, v2 and v3. So everything is connected with the neural network. So we'll have a simple Markov model. We'll have like this different clusters of distribution, each having a Dirichlet mixture. Okay. So there are higher levels of evolution even. So generally this is a question of about how and what would a higher level model of evolution be look like. So generally we will have like multiple alignments which are produced at different times in course of the evolution, and generally for the case of every 100 million years we will have this multiple alignments across different evolutions. So generally this distribution evolves over time, and generally this evolution takes place on the distribution over several distributions. So we'll have this emission distribution to be considered as a Dirichlet mixture. We'll have P of P is equal to summation over I lambda I d of alpha I q I of P, and we'll have a Markovian substitution process which is operating on the QS. Okay. So we'll have like AS and lambda S, which are the additional processes to the Markovian substitution process. So this is the extension. So we'll have P of P is equal to summation of I lambda I of T d of alpha T q of I of T of P. So with the case of PAM matrix substitution model, so this QI is chosen equal to the binary unit vector. So the hidden Markov model emissions is actually regularized so that the model is actually consistent with the case of the PAM matrix columns.